Okay, we are live after forgetting to start the previous record for all the millions or even billions of viewers out there. Yeah, from Brasilia and everywhere, and Sydney, Melbourne, and so on. Yeah. Okay. So, yeah, so the previous lecture, I think I will record it on my computer later. So to all my billions of viewers, don't be afraid. Okay. So let me give, so examples of bases that are the standard. So examples of so let there be commutative continuity, unity, and V, M, and N are integers. So the vectors E1 equals to 1, 0, and En 0 to. So the standard basis tuples are there form a basis of Rn. I denote these matrices. So AG is the matrix. So everywhere is 0, but we have on the E. So here's the ith node, and here's the ith row and the jth column. We have 1, and everywhere else we have 0. So we have 0, 0, and zeros everywhere. Sorry for the very strange diagram, but this is a basis of set of matrices. It's for EG from 1 to M, E from 1 to M, and G from 1 to N. They are a basis of space of matrices. They need to be more specific with smaller dimensions. Okay, for example, if M equals N equals 2, we have E11 is this matrix, E12 is this matrix, E21 is this matrix, and E22 is this matrix. Empty set. So the empty set is a basis for the zero vector space. So the zero vector space has no basis because it's a zero dimensional space. It's a basis for the zero vector space. So the zero vector space has no basis because it's a zero dimensional space. It's a basis of the zero vector space. Oh, zero. Okay. And if S is a set, it is a basis of the free vector space defined by it. Then S is a base of free RS. So the space of formal linear combinations is defined exactly by linear combinations of this. So if you have apple, orange, and banana, we have basis from apple, orange, banana formal base of the linear combinations of these elements. Okay. Okay, polynomials, but they are also free vector space. Okay, in particular, if the set S is 1x, x squared, and so on, is a basis of free Rs, which is the polynomial space. So yeah, it's R of x. So all the monomials form a basis for all the polynomials. Any polynomial is a linear combination of monomials. Okay. So this is enough for now. Have a proposition. I will not prove. Maybe, I don't know. So let R be a commutative ring with unity. And V is be an R module. And the set S, so it is a subset of V. So it's a set of vectors, be a basis. Yeah, okay, only this one. Then, so a basis is a subset, usually very small one of the set of all vectors. And only this one, so S is. So then S is a basis of V if and only if double F, if and only if any element, so any element of V has unique expression, a unique expression, any element v. So v and v, make expression v equals lambda 1 e1 plus n en, where these are basis elements, e1, en are in S, and lambda 1, lambda n are in R. So any vector can be expressed in a unique way by the basis. This is the essence of this theorem. Okay, shall we prove it? We haven't proved anything today so far. So let's prove it. Okay, let's prove it. Test some the language. So first we prove that so S is a basis, therefore unique representation. This is the first part. Okay. So for simplicity, I will assume that S is finite. Not that it's much different, but anyway, we are mostly interested in finite dimensional spaces. So for simplicity, let S be finite. And write it this way: S equals E1 to En. And take V in V, and we need to prove that it has unique representation. So we need to prove that we need to prove two things. First, that there exists lambda 1, lambda n, such that V equals lambda 1 E1 plus lambda n En. This is span, the definition of the requirement of span. And that any so it has we need to prove that it has a representation, and two, that this is given by definition. So I just two, that if V equals lambda 1 E1 plus lambda n En, and also equals to mu1 E1 plus mu n En, then all of these are equal. So lambda 1 equals mu1 and lambda n equals mu n. But this is okay, indeed. One is the requirement, is the condition. One is the requirement that E1 to En span V. So by definition, a set of vectors spans the whole space if any vector has this representation. And 2 is equivalent to 2 is rephrased as so 2, because if we subtract them, 2 follows from the following. So lambda 1 E1 plus lambda En equals to mu1 E1 plus mu n En is the same as when we subtract them, lambda 1 means minus 1 E1 plus and so on. Equals to 0. But what does linear independence tells us? So yeah, but by linear independence, we have that lambda 1 minus mu1 equals to 1 and so on. Lambda n minus mu n equals to 0, which is what we want. I.e. lambda 1 equals mu1 and lambda n equals mu n. The other direction is very similar. I'm not doing it. I wanted just one. So if you want, you can try similar. Again, the first condition is by default definition of span, and the second one is when we subtract, as we see, two vectors to have the same representation. Naturally, is rephrased as linear independence. Okay. Let's go maybe to. Okay, let's now talk about subspaces. For definition. Let R be an commutative ring with unity, V be an R module, and W is subset of V. We say that W is a subset, is a subspace, a linear subspace. Okay. Linear, yeah, maybe a linear subspace. Sometimes the word linear is omitted. Of V if it is a vector space with the restricted operations. It's a module, sorry. If it's a module with the restricted operations. Like subspace. Okay, submodule, yeah, maybe. Okay, not linear. Okay, let me call it submodule. I'm not sure. Maybe subspace will also be fine. It's a module with the restricted operations. Equivalently, this is a claim, but equivalently, okay, so so again, start with an commutative link with unity. V an R module and W. Then W is a submodule. Of V if and only if these two conditions. We have two conditions. So first, it can be rewritten as a single one if I write it's a single one for all lambda mu in R and V W in V in W. We have lambda V plus mu W is also in W. So a submodule is a space closed under linear combinations. So I haven't defined. Okay, so let me give some examples. There's two standard examples that I will later generalize. So examples. So consider let be a commutative link with unity. And be an integer. M and N are integers. And A be a matrix. Then, first example. So W is the space, is the null space of A. So it's the null space of A. So the null space of A is the set of all vectors in Rn such that Ax is the zero of Rm. This is the null space. So this is W is a submodule of Rn, and it's called the null space of A. The null space. Okay. Let's prove it. So indeed, let x, lambda, and mu are in scalars and take two vectors in W. X and Y are in W. What does that mean? So i.e. ax equals ay equals 0. Then a times lambda x plus mu y. What's this? How do I expand that? I have a matrix times some combination of vectors. How do I matrix times some combination of vectors? How do I expand the term? Yeah, so this is distributive property. So this is lambda a of x plus mu a of y. And this is 1, so this is 0 and this is 0. This is lambda times 0 plus mu times 0, which is 0. So it is closed under linear combination. This is the definition. See? Not definition, but the proposition that shows this thing. And the other thing is called the image. So this is another, let me call it a different name. Let's, for instance, Z. Z is the image of A, which is the set X such that where X is in Rn, and so this was a subset of Rn. This is the same as all vectors in Rm that can be expressed by this thing, such that there exists X, not Y, yes, X in Rm, such that in Rn, sorry, such that Ax equals Y. And this is a subset of what? Of Rm. So this thing here is a submodule of Rm. And again, we proceed the same way. So indeed, let lambda and mu are scalars, and we take two vectors. Let me call y1 and y2. I don't know, y1 and y2 are in Z, maybe Z1 and Z2, doesn't matter, in Z. So, because they are in Z, we have to choose x1 and x2. So choose x1, x2 such that ax1 equals we're expanding the definition right now. such that ax1 equals e1 and ax2 equals y2. Then when we take the linear, apply a linear combination. Also, we need to prove that lambda times y1 plus mu times y2 is also in Z. Which means that let's call it this thing called y, i.e. there exists x in Rn such that ax equals y. Can you tell me a vector x that satisfies this property? So I expanded the definition. So first of all, y1 is ax1, y2 is axy2, and I'm looking for some vector that, when a applied to it, gives y. What should? Yes. Well, take x equals lambda x1 plus mu x2. Then ax is this thing here, and we expand by linearity, so this is lambda ax1 plus mu ax2, which is lambda y1 plus mu y2, which is y. Okay. And hence Z is the module. Of M. So this is a little bit harder because there is existence and we have to choose and like that, and we have to guess what x should be, but it's in modules vector spaces usually it's not, the choice is usually a natural one. Okay. So let me give some examples. A more concrete one. For instance, A is the following 2 by 2 matrix, maybe. Okay, let me just give some. So this is matrix with 2 rows and 3 columns. And the null space of A is the set of all x1, x2, x2, x1, x2, x3. So it's the all x R3 such that ax equals 0. Okay, so let me solve it. So let x equals x1, x2, x3. And then we get the following system. I don't know how you studied. Oh, as this is in, let's say, rationals, for instance. I don't know. So are you aware of this notation and solving? And so I multiply this by here by 2, and we get 1, 2, 4, 0, 0. Sorry, this is -8. So this line is destroyed. So we get that 1x1 plus 2x2 plus 4x3 equals 0. And let me, for instance, represent x1. So x1 equals minus 2x2 minus 4x3. So we have that the null space of A is the set minus 2x2 minus 4x3 x2 x3. In Q. This is how you solve linear systems. So it's a vector space. Yeah, it's a vector space from the previous example. I haven't spoken about dimension. Well, it's two-dimensional. I'll talk about the talk about dimensions later. Let me find the image of A, or I'm not sure. Maybe some authors use range, but image is also fine. Image of A is the set of vectors x in R2 such that, okay, I will write it this way. X in R2 such that there exists y in R3. This is y, this is x. Such that ax equals y. So so we are looking for what? Pairs that for which this system has solution. Sorry, but I have it's not a, I have fixed the link, so everywhere instead of generic R, I can use the rationals. So let y be y1, y2, and we are solving x1, x2, x3 equals y1, y2, which is equivalent I suppose everyone here has studied standard linear algebra, has solved such kind of problems. This is -2, -4, -8, y1, y2. And again, I multiply this by 2. And so I get 1, 2, 4. A Gauss method. And 0, 0, 0, y1, 2y1 plus y2. So what should I conclude? So this 0 times something plus 0 plus 0 equals this thing here. So this is, yeah. Yeah. So 2y1 plus y2 equals 0. Therefore, y1 equals minus 2y1. And so the image of A is the set of vectors. And this has always solution. I can just pick this and this to be 0 and this to be 1. Is the space y1 and minus 2y1. Where y1 is a rational number. Okay. And we don't have any time for anything else. Okay, any questions about this thing here? Here I will work with a field. It can be a little bit different if I work with a known field, because the standard Gauss methods usually requires me to divide sometimes, and if I cannot divide, there may be problems. But this is fine for the introduction. And yeah, I mean, I will work with some non-field modules in the future, especially those that are defined by sets of functions, but there the subspaces will come in different ways, not in this standard way of solving linear systems. So I just wanted to illustrate subspaces and null sets and images and so on. Next time we will continue with linear maps, which will generalize this thing with instead of matrices, we will work with linear maps. Okay. Maybe you could